So 3.5 is similarity and diagonalization. So just the definition first. So square matrix, again, all of these are to do with square matrices, are similar. So we say that two matrices are similar if they have the same determinant, characteristic polynomial, and eigenvalues, which is actually not even necessary to say, because if two matrices have the same characteristic polynomial, then the eigenvalues are the same, because that's how you find the eigenvalues, right? But that's the actual definition, similar, those three. So if A is similar to B, then there exists a matrix P so that we can multiply in this order, P inverse times A times P, and get B as the answer. And a Q so that we could do the same thing. Now that's going to be useful, and it's going to, P and Q are found using the eigenvectors. So that's why this sort of follows that. All right, so we're going to use similar matrices to find powers more easily. So for example, if you wanted to take this to the fifth power, how would you do that? So if you had a matrix to the fifth power, you would write out 5 of them. You multiply the first 2, get an answer, then multiply that by the third, then write out the answer, multiply that by the fourth, write out the answer by the fifth. So if we had to the 20th power, right. So there's a quicker way to do it, and that has to do with eigenvalues and eigenvectors. So a matrix calculator, maybe. Right, so you do this first, and take the answer to that with this one, take the answer to that with this one, take the answer, right. So it would take a very long time. But there is quicker ways. So not that we're going to do this example right now, that's later at the end of the chapter, we figure out how to do that. But if we had this matrix to the fifth power, let's actually do it. We're not going to calculate this first one, but let's calculate a diagonal matrix. So you see this is a diagonal, because it has numbers on the diagonal and zeros everywhere else. That was the definition. Diagonal matrices are actually easy to find the powers for. You don't have to do it out 5 times, because let's do it just squared first. So what do we get when we square this, multiply it by itself? So 5, 0, 5, 0. So 5 times 5 is 25 plus 0. Then our first row with our second column, 0 plus 0. Our second row, 0 plus 0. And our third row, 0 plus 3 times 3 is 9. So do you see what happens if you actually square a diagonal? It's just the diagonal squared. So what if we had cubed? What do you think? There's squared, and then times it by another one. We end up with 25 times 5, which is 125, 0, 0, and 9 times 3 is 27. Right, which is 5 cubed, 3 cubed. So what would 5003 to the fifth power be? Yeah, you could write the number in if you wanted, but yeah, to the 5, right? I mean, if it was to the 20, you're not going to write the number out, so you can leave it as a power if you want to. This one's not too bad, I agree, so you could write the numbers. but a diagonal. So that's what we'll use later, because when we get the eigenvalues and eigenvectors, that P matrix that we were talking about up here is going to be a diagonal matrix, and we're going to use that to actually find the answer. So we'll use this later, but I just wanted to point out that if you are doing powers of matrices that are not diagonal, they're hard. They don't end up being just squaring them. You end up with numbers that aren't as nice, but if they're diagonal, they do end up being nice and easy. Okay. So the process is going to be to find a matrix D, which is a diagonal, similar to A. So think about that for a second. If we found a diagonal that's similar to A, then what do they have in common? So similar matrices have the same characteristic polynomial, the same eigenvalues, same determinant. Okay, so we're going to find a diagonal that's similar to A and use actually, let me write it this way. So a diagonal matrix that's similar to A. So then we would say that we could write, we don't know what P is, but P inverse times A times P and get D. How could we rearrange this to solve for A? So we've done this before. This is not new. You can't divide by P because that's not legitimate. How do you get rid of the P on the outside or the end of this? What do you do to both sides? If we want to solve for A. So if we want to solve for A by itself, we need to multiply by P inverse on the outside, or on the end, right? It always, so why would that help? What's P times P inverse? I. So now we have D, P inverse equals P inverse A times I. Anything times I is itself. So this is D, P inverse equals P inverse A. Right? Because anything times I is itself. So now how do we get rid of the P inverse on the beginning of it? Multiply both sides by P at the start. These cancel or equal I. And so we get A is equal to P, D, P inverse. So we're actually going to use that, which is rearranged of the other one. I didn't want to jump right to this because the actual similar matrices starts with P inverse AP, and then D is similar to that. If you rearrange it and use the same P, then it's the other way around. You see that P comes first and second. So you actually do have to remember which order they come in when we do this, okay? Which I'll show you after. So a matrix is said to be diagonalizable, able to be diagonalized. If it is similar to a diagonal matrix. That is, if we can find P and D such that P inverse A P is equal to D. Or rearranged. Okay. So that's what we're going to try to do. So some matrices, they can't be diagonalized. So D is actually the diagonal matrix with n eigenvalues down the diagonal, zeros everywhere else because it's a diagonal matrix. And P is the matrix of corresponding eigenvectors. So, for a 2 by 2, this is easy. So, we're going to do it for a 2 by 2. Okay. To start. So this is what I'm saying, that sometimes I won't make you find the eigenvectors and the characteristic polynomial, I just give them to you, so you're halfway through the question. Okay? We actually did this matrix earlier, so we did find the eigenvectors already. So for lambda 1 equals -1, we would say V1, vector 1. So if you write subscripts, you'll remember which one goes with which. I think we have, let me look back. This was the first one we did. And for one, we had the eigenvector. I thought we did this one. 1, 4, 2, 3. So for 5 it was 1, 1, and for -1 it was -2, 1. Okay, so we did that earlier. And we got these vectors. So you could go through that whole thing. So we say that so D is the diagonal matrix with the eigenvalues down the diagonal. So in either order, but you just have to keep the vector, corresponding vector in the same order. So if we put a -1 and 5, so I did lambda 1, lambda 2 here, then the P would be vector 1 that goes with this one, -2, 1, and then vector 2, 1, 1. Okay, so this would be lambda 1 and P is vector 1, vector 2, so the same order that you write those. Okay. So A equals P, D, P inverse, I wrote that down before. How could I get this from that? Right, the P on the end, and a P on the end would make those cancel, right? If I multiply this by P, and this by P, they cancel, so AP equals PD. So that's a check that you can do. So you can do A times P, multiply those, so A times P, and then do P times D. And you should get the same thing. So just a note, we need n distinct linearly independent eigenvectors to diagonalize. So there are cases when you wouldn't have that. So say, for example, you had a 3 by 3, you ended up with only one eigenvector or one eigenvalue, and then maybe 2 corresponding eigenvectors to it. You need to have 3 in a 3 by 3, not just 2. So the example we did earlier, we did 2 3 by 3s for the eigenvalues, and the first time, how many eigenvalues did we get? For that first 3 by 3 we did. For the first 3 by 3, not that crazy long one I did on my own. But that first 3 by 3, so I'm going to show you the notes for that. So here's the first 3 by 3 we did 2 videos ago. So here is our matrix. We found the eigenvalues, and there was only 2. And that's okay, as long as when you find the vectors, there ends up being 3. So is there 3 for this? When we found the vectors for -3, we ended up with 2 vectors. 1, 2. And for the next one, 1, we ended up with 1. So how many vectors is that altogether? 3. So this one would be okay. So how would we diagonalize that? The value that has 2 of them just gets written down twice. And I'll show you that. Now, what about the other example that I did on my own, that big long one? We didn't go through and find the vectors, but here it is, the 3 by 3. So there's the 3 by 3. This was that big long one that I did it without factoring, and I found 3 eigenvectors, and as long as they each had one, or I found 3 values, and as long as they each had 1 vector, you could diagonalize it. But if one of these had 2, that would be too many, and you can't. Yeah. So you have to end up with exactly 3. The values itself doesn't matter, it's the vectors. That's how many vectors you end up with. So we'll write these down after, but this is what this note says. So the note says we need n distinct eigenvectors, not eigenvalues. You don't need to have 3 different eigenvalues when you're in a 3 by 3, but you do need 3 different vectors. Okay? And just by doing it, when you get 3 vectors, they are linearly independent already. Okay, so you actually don't need to check that, they already are, but you do need 3 of them if you're doing a 3 by 3. Okay, so here's a vector, or a matrix, already looking at it, hopefully you see that it's a little easier. There's already 1 0, and the numbers are smaller. There's not a bunch of 7s and 8s, right? The numbers are a bit smaller. So we're going to go through and do this one, okay? So if we need to diagonalize, I didn't give you the eigenvectors and the eigenvalues, so we need to find them. So first is A minus lambda I. And that is subtracting lambda, oops, from the diagonal. So just subtracting lambda down the diagonal, leaving everything else the same. Now we need to do the determinant. So first, before you do the determinant, is there a row operation that makes a 0 here? Easy enough. I just see one possibility. Looking for those same places that we did the zeros before, using these 2 rows to make a 0 here, like sort of ignoring that, and then these 2 to make a 0 in one of these spots. Same idea as we did before. So if we wanted to make a 0 right here, what would the step be? Using this one. So this is in row 1. It's a positive 1. This needs to be a negative 1. So negative row 3 plus row 1. And that would be the only step. It gives me 2 zeros, and then it ends up not being too hard to find them. So minus row 3 plus row 1 or lambda minus 16 if you want. I just want to double check before I did anything else. So here it is, and then I would just go and find the determinant from here. Okay, so you're going to end up with that 3 big equation. So let's write determinant here equals. So our main diagonal, 1 minus lambda, 1 minus lambda, and 4 minus lambda. Then the off diagonals are going to be 0 because we got those two zeros there. So this one is 0 times 1 and 0 times that. Then backwards, lambda minus 16 times 1 minus lambda times 1. The 0 one is gone, and the other one is 11 times 1, 11 times 1 times 1 minus lambda. Okay, so carefully doing your diagonals. We've got 3 terms. You see it's a little bit nicer. We've got 3 terms. Just put that minus in, fix it up a little, and do all 3 terms have something in common? What do they have in common? Okay, so this is more likely how it ends up. You might need to make 1 0, or you might not even need to make a 0. When you do it, you've got 3 terms, and they do already have something in common. You don't really need to do a lot of maneuvering, okay? What do they have in common? 1 minus lambda. So there's one of the factors. And then write out the other ones. And I would just, you could just multiply this out and you've got a quadratic. So let's do it that way. You've already got the cube gone because we factored one out. So now what's left is a quadratic. So if we multiply this out, so 4 minus lambda minus 4 lambda plus lambda squared, lambda plus 16 minus 11. Join the like terms. So lambda squared and the lambdas minus 6 and the constants 20 minus 11, 9. Okay, so that's what I meant by once you get one of them out, multiply everything else out and you can factor it. Okay, and that's much shorter. The other one, remember that second one I did was like a whole page. Usually you wouldn't have to do all of that. So what are the eigenvalues? 1. And here, just 3. That we actually say this is multiplicity too. Right. So if you ever see like multiplicity or something, that's what they're asking is how many times did that one occur? So if it's, yeah. So you can have either 3 distinct, they would all have multiplicity 1. You could have 2 and 1, or you could have all 3 the same if it factored that way. And then that would have 1 eigenvalue, multiplicity 3. All right, so once you find the eigenvalues, you find the eigenvectors from that. So for lambda equals 1, oops, okay, so going back to our a minus lambda I, plugging your 1 in. This is weird. Okay, and then row reducing. So, this isn't going to work, which is fine. So, this is row 3. We want a 0 here, so you would do minus row 1 plus row 3. And we end up with 0, 0, 15, 0. All right, now what? This is a good one. I like it. It's weird. What do we do next? Not the 15. So you make a 1 in the first row, that's here. So this is now a lead position, because there's a lead 1. Then you go to row 2, and the first non-zero number, we haven't seen one like this since the first time I introduced row reduced echelon form. So the first non-zero number you come to needs to be a 1. So it doesn't have to be in this spot, it just usually is. It doesn't have to be. So here needs to be 1. So that's in row 2, we need to divide by 11. And then, once that's a 1, above and below, so that's now a lead 1, above and below have to be zeros. So this is row 1, that's a negative 12, so the 1 needs to be a positive 12. And row 3, that's a positive 15, so the 1 needs to be a negative 15. And there's our row of zeros.
Wouldn't that negative 15?
Yep, negative 15, row 2. That'll be a negative 15 adds to a 0, 0, and 0, 0. Nothing else changes when they're all zeros. See it? Okay, so where's our lead? Lead here and lead here. And y does not have a lead 1, so this is free. So y is t. The z is free, is lead because it has a lead 1. When we write out the 2 rows, this would be x plus y equals 0, and here will be z equals 0. And y is t, so this will be minus t, y is t, and z is 0. Minus 1, 1, minus 1, 1, and no t's. Okay. So our second lambda value is 3. So plug 3 in to a minus lambda I, and we will get 2 minus 3, 1 minus 3, and 4 minus 3. 1 minus 3, 1. Yeah. So I just plug that in to a minus lambda I. I could see it up here at the top of the page, right there. So I just plug that in, and then we row reduce. So how do we row reduce this one? You can switch rows too, that's fine. We want a 1 in this top spot. I probably just wouldn't bother, I would change all the signs. Row 1 is minus row 1, or divide by minus 1. And we want this to be a 0. It's in row 3. It's a 1, that's already a negative 1, so row 1 plus row 3. All right, so that first step will give us and you can, of course, write the step out on the side, but that's what it would give us. Then, what would be next? This we want to be a 1. These, you can see that will end up being a row of zeros. You could do it right now or later, it doesn't really matter. Row 3 would be row 2 plus row 3. This one is not as easy, I'll do it after. Okay. And one more step. This one. So that's in row 1. It's already opposite sign, so row 2 plus row 1. Okay, so 12 is 24 over 2 plus minus 11 over 2 would be 13 over 2. Okay. So we have a lead for the x, a lead 1 for the y, and this would be free. So z equals t. We would write it out. X plus 13 over 2 z equals 0, and y minus 11 over 2 z equals 0. Oh, thank, plus 11. Oh, yeah.
The 11 was the thing, oh.
Yeah. Move them to the other side. So, minus 13 over 2, 11 over 2, and 1. Okay. All right. So, for this part, we had lambda 1 is 1, and the eigenvector, and lambda 1 equals 3 with eigenvector. And let me just say that I would normally do this. What did I just do? Do you see that at fractions? It can be any multiple, so I multiplied by 2 and got rid of the fractions. So I just multiplied everything by 2.
So why did you?
Well, I changed it to r because now it's a different t. Like I multiplied it by 2, or you could put 2t, right? Or I just multiplied it by 2. So it wouldn't matter, you could still put t, but if you're putting equals, it's not the same t anymore. Different by 2. So I just changed the letter, but it doesn't really matter. But if I were using the vector itself, I would get rid of the fractions and use it instead of... Now, so the question is, it was to diagonalize. It wasn't to find the eigenvalues and vectors, which is what we just did. If it asked for that, we would stop and we found them. To diagonalize, though, what has to happen? At 3 by 3, we need 3 distinct, linearly independent, means it can't be a multiple of each other, eigenvectors. Do we have that? No, we only have 2. Because we found 1 here and 1 here. That's only 2. So A, in this example, cannot be diagonalized. Okay, so just showing you one that can be diagonalized. We're not going to solve another one all the way from the start, but we will write the one down that we have the answers for already. Okay, so the one that we have the answers for, that we did earlier, is So here is the vector. We found the eigenvalues. There was 2. The first one, when we did the vectors, there was actually 2 vectors. This is a plane. And for the second one, 1 vector, a line. So we ended up with 3 distinct vectors, even though there's only 2 eigenvalues. So to diagonalize, we say that the diagonal is, in any order, negative 3 has to be listed twice because it has 2 vectors. So we would say negative 3, so there's a diagonal. You could put the 1 first and then the 3s, it doesn't matter. Whatever order you put it in, though, your P is in the same order. So for negative 3, we have these 2 vectors. So you would say negative 1, 1, 0, negative 2, 0, 1, and then for the 1, we have negative 2, negative 1, 1. And how would you check? AP equals PD. Multiply A times P and P times D, and you should get the same answer. All right. So what we're going to do next class is we're going to take things that we can diagonalize and learn how to figure out powers using these. Okay, so that'll be next class. But the homework for both of these sections will be there. The only one you wouldn't be able to do is just the question that says find A to the 20th power. That would be it. Otherwise, everything else you'll be able to do in the homework. So you should look at those before next time.